ABW Cafe. This month we have Joaquim, who's going to be giving a wonderful talk. So without further ado, I will hand it over to Joaquim.
Hello, everybody. So good morning, good afternoon, or good evening, depending on where you are watching from. I was already nervous, but now I just got a bit more nervous because Kate said that my talk is going to be wonderful. Well, we will see whether it's going to be wonderful or not. The reason why I was nervous is that I've seen this talk being advertised on so many diverse gremium that I expect the public in the end to have different expectations. It's always difficult to serve public with known expectations. I think it's even worse when we do not know upfront what people expect. But let's see, I did prepare something and I'm going to serve it to you on this cafe. So without further ado, my name is Joaquim Gromicho. I've been with ABW for quite some time, and I've done beautiful things there. I'm very proud of those, and mostly what I've been doing there relates to optimization. I will be sharing some thoughts on the topic with you. So let's see, I prepared a slide deck, and I think that slide deck is gonna be on your screen, I guess now, and it's entitled, How Does PISA Find Optimal Locations? I guess that many of you may know what PISA is. If not, there will be, of course, a PDF of this slide deck full of areas where you can click, like this one. And if you follow such links, you end up finding, for instance, that PISA is a repository called Public Infrastructure Service Access, full of Python code to do many things, including optimization. And what is a very important aspect of PISA is what is called access. And I will try to start my talk on optimization in PISA by talking about what is access. So it all starts with a good accessibility metric. And I will try to tell you in the beginning why a good accessibility metric is important. So I like examples. And I'm sharing an example with you that I happen to know a little bit about, because this is an health center in Nepal. I've never been to Nepal. I was at a Nepalese restaurant yesterday, by the way. That's the closest I got to the country in terms of really tasting what it is there. But I have been involved with Nepal together with other people from ABW. In the time of COVID, we were trying to help Nepal finding good ways to determine the locations for their test centers. So this is one of the health facilities that is being running in Nepal for quite a long time. It's there somewhere. And what I think it's important to realize is that having an health facility somewhere actually means that it should be available to serve population. So the somewhere is something that we can actually explore from our desks. So we can just go to, for instance, Google Maps, realize that this health facility is right over there. And that's, of course, part of the world, part of Nepal. But what does that mean for the populations around it? So let's go back to my deck. From the code in PISA, one can actually produce pictures like this. It resembles the Google Maps picture that I've shown, but it was actually produced with a little bit of Python, showing that exactly same location on a map, and that map is, of course, of the same area. All right, so there is that location over there. We also know where the population is, and what we want to know is who can reach that population within some reasonable metric. Well, one could think, okay, a reasonable metric can be something like a circle around that location. I think that many of us would find that reasonable, right? So we have a point, we have a kind of a distance that we consider to be a reasonable distance to be able to reach that point, like 10 kilometers in this example, and there is this circle around it. All right, well, real life offers many difficulties to access, And I think that there are many places with very challenging geography, and Nepal is definitely one of those. So if we would take the same distance, like 10 kilometers, but do not measure it like I'm doing it now in an Euclidean way, there's equally distance points following a straight line, but following the infrastructure available at the country, like the roads, the trails, everything that one can traverse while walking or driving, we end up realizing that 10 kilometers around that specific point is not that circle, but it is this shape that we see. Thus, any point on that area is within 10 kilometers of reasonable traveling conditions to that specific point. It's very different from the circle, meaning that the real life accessibility of those around that point require care to be measured. And one can say, okay, distance is one thing, travel time is a different one. 10 kilometers, well, at least in the Netherlands, 10 kilometers is something that we can walk in 1 hour. Well, if we say, okay, what about 1 hour of walking? Well, then the area becomes much smaller. And you see that the importance becomes obvious of having indeed quite a good metric to define whether a point is accessible or not. So if you look at this superimposition of the different metrics, you can see that they are all very different, meaning that points within that yellow circle may indeed be or be not within reasonable access metrics of that point, of that hospital over there. Right, so this is one important thing that PISA needs to cover, and it all comes down to computing travel distances or travel times on real life networks. And that is part of optimization in some sense. Well, while preparing for this talk, I realized that there will be a lot of things I cannot cover. So I like to at some point, I will like to tell you that I will include many additional sources and they will be accessible from the slides. But we start right now addressing the question, how does one actually compute such distances and travel times? Well, it happens to be a very well-solved optimization problem. And a very well-solved optimization problem that has been solved for many, many years. And one thing that I always like is to try to learn by doing. So as I said, the deck will give you a lot of links to things that you can explore, and some of them will allow you actually to do things, to do optimization by yourself. So the very first thing I share is a book that I authored with 3 friends. And this book tries to, it will be published as a textbook soon. It is now available as a preview that you can actually download from here. This book tries to enable you to use optimization in a way that is somehow easy to deploy if you know a little bit of Python and if you are able to think in an abstract way, translate some kind of reality that you want to optimize into a mathematical model, which is not easy to let's say to explain what it is without a number of examples and some stories behind it. So the book is basically a collection of stories that you can read and relate to your reality and try to apply. There is a lot in it. I will not go through it thoroughly, but I will also refer to something that complements the book, which is online and includes many of so-called notebooks, which are a collection of text and code written in Python in this case. And this particular one will enable you to actually do shortest path computations on real-life networks, including sophisticated things that I will mention in a moment, which are part of PISA, in fact, because, as I will explain, PISA will need to have not one, but many of these travel times and distances. And one of the things that is used there is actually explained in this notebook. But let's go back to the deck. So shortest path is computed on networks. That sounds not much like real life, but what is the way to bridge a situation in real life to these mathematics that are involved in networks and this shortest path thingy, which is an example of an optimization problem solved by an algorithm? Well, if we look at the Netherlands, and I'm actually on this blue dot over here, and the headquarters of the ABW are over there in that place called Amsterdam. If you look at the Netherlands from above, like from a satellite or something like that, it looks like what you see here, except for the text and the lines, which was superimposed on this photo. So there are some green areas, there are some not so green areas, there is maybe some water, there's a lot of water in the Netherlands, but this is not good enough to do optimization in terms of accessibility. You need to go from this reality to somehow simpler way to look at it. So there could be a map like this one, but this is not yet enough to apply mathematics, to have a model, because basically what mathematics does is to model reality in some way that enables the problem to be well specified and the solution that we seek to be found. So this is not yet a model, but it's one step towards a model. And then in fact, what becomes a model is the collection of all these roads and alleys and highways, all these, let's say, infrastructure that enables us to travel into a collection of lines and points. And a collection of lines and points, and this is still the Netherlands, but it looks much more dull and boring now. But this is the moment that we can actually resort to mathematics. And when we can resort to mathematics, we can solve problems, and we can solve problems in sometimes optimal ways. So basically what we always need when we are dealing with accessibility is know how long it takes to go from one point to another. And in fact, we know how to do that already since 1959, because this gentleman published a paper, and the paper, you can find it if you follow this link. This paper was published indeed in 1959. It has an amazing number of pages, 3 pages, and it solved 2 problems. It solved not only what we call the shortest path problem, it also solved this, or it also explained how to solve another problem, which is called the minimum spanning tree. So 3 pages, 2 problems. It's quite amazing. And it's also amazing for those among us that relate to this type of works, that it has already reached 15,000 citations. So there are many, many people that read these 3 pages and decided to do something with it. All right, but what is the essence of the method invented by Professor Dijkstra, which enables to find the best way to go from one point to another using the available infrastructure? As I said, the available infrastructure can be modeled as a collection of points and connections between those points. So I have these blue dots, which are some points on my network, which represent some locations in real life. And I have these arrows with those numbers in them, which represent whether or not I can go from point A to point B, and what it means to go from point A to point B. It can be that 10 is a distance, like for instance 10 kilometers. It can be that 10 is a traveling time, like for instance 10 minutes. So it's all a question of which data has been used to represent this network. But regardless of what are the choices made, if I have a network, then I can actually ask myself the question, how can I go from, for instance, A to C in the shortest effort possible, being that either distance or travel time or whatever, represented by the numbers on those arcs or those connections that we see. All right, so actually what Professor Dijkstra told us is that the way to do that is an application of an algorithm that may be easy to understand. If you are at your departure node, like at A, then you know that you have already reached it with 0 effort. So at A, you have spent 0 and you are already there, but you want to reach C, so you do not know yet how long that will take. But from A, you know how long it will take to reach those nodes that have a connection from A. So from A, you can reach B in 10, because there was the 10 over there. So you add that 0 that was information at A with 10, and you reach it in 10, or in 5, and then you reach D. Those are the two ones that you can reach. And then what the algorithm says is the following. There are some mathematical assumptions behind this algorithm, and the most important one is that there are no negative numbers involved. Well, in real life, when we deal with accessibility, there are no negative distances, there are no negative travel times. Well, in mathematics, we could have networks with negative numbers, but they are out of scope for now. So if there are no negative numbers involved, then the following will always be true, namely, the number that we have computed so far, which is the lowest, can never be improved afterwards. And then basically what you say is, I move from A to D, and I do it again, and I update the information on the other nodes, and I will look for that one, which is the lowest, which happens to be E now, and I do it again, and I update the information on the other nodes, and basically now I know that I can reach my destination C with a path of length 13, because that's what I already found. But since there is yet another node with a lower number, I need to check it first, and I end up updating indeed my length of reaching C to 9, and the algorithm terminates now because I cannot find any improvement anymore, because all the nodes have been explored in this particular case, very small case. And then the algorithm will give me this path, which goes from A to D, D to B, B to C, and it has a length of 9. And this is something that we can do already since 1959, and it's in the heart of all these instruments that PISA applies to find accessibility metrics using road networks, which are translated to actually big instances of things that look like this drawing here with nodes and arcs. All right, so I do not know much about my audience. This talk was advertised among large groups of people. May in my audience somebody be inclined towards computer science and like to program, then you may like this notebook. This notebook is not yet part of the online companion to the book that I referred to. It basically shows you how you can very easily implement the problem of solving a shortest path in two different ways, one of them being the method of Dijkstra, including an implementation for the method of Dijkstra, which is very straightforward, like here, and an implementation for the method of for the same method, which is more sophisticated because it has a very powerful choice of data structures, and also some timings showing that this very sophisticated choice indeed yields neglectable running times. In these graphs, I have here the running time of this method for increasingly bigger networks. And you see indeed that this all goes very efficiently. So then you would say, okay, 1959, it can be implemented with apparently not much code. I can go there and I can check it. So we are done, right? So now I know everything I need to know about accessibility metrics. Well, not quite. It is true that we have detailed digital maps. Well, whether they are detailed or not depends on the area of the globe that you are interested in. Some countries have indeed very detailed digital maps. Some other countries have less detailed digital maps, but that's what you actually need. You need some kind of digital map that it will translate into a network. And if you have the network, you can apply these algorithms or algorithms like this one. And then, of course, if you have the candidate locations where you may or may not install some health facility or some other service of some public service that requires installation in order to serve population, then you have like the ability of deciding whether the potential users of that service are within what you consider to be a reasonable accessibility threshold. And then you can define what I will be calling the catchment areas for these potential locations. So a visualization of such a catchment area for that hospital in Nepal was either that yellow circle that I've shown in the beginning, if we would consider that it's reasonable just to fly from one point to another following a straight line, or those more fancy shapes which require that you travel on roads, and you either are interested on the distance or on the travel time. And then, as I said, you compute such values using algorithms like the method of Dijkstra. Okay, so then you will say, okay, I have that, it's efficient, I've seen a network, I've seen a notebook with some code and with negligible running times, so I'm done, right? Well, not quite. The method of Dijkstra, as you may have seen on that small example of mine, while looking for the shortest path from one origin to a destination, is actually going all over the network, and then it's happy when it finally reaches the destination. So it's fast, but there is a kind of a waste of time over here. There is also a benefit here because, as you can see, you know a lot. You have computed a lot of shortest paths with one single go. But if we want to have a feeling what that means for a very big network and a very big number of locations that you are interested in, let's do some back of the envelope computation. PISA does not work like a GPS system in your car. We don't need only one single query, like going from my departure node to my arrival node, or going from my home to my work, or whatever the example may be. It requires to have like all these potential households in a country related to all these potential locations to install a facility in a country or in an area or whatever. So if I have a simple back of the envelope computation, and if I have just like, for the sake of simplicity, I will have like as many households as I have potential locations. So if I have like 10 of those, I need the distances between the pairs of each of those numbers, and that's like 100 of them, of those pairs. And if I normalize my algorithm of Dijkstra, like taking 1 second, and well, it takes less, but every normalization is good. Like taking 1 second for every query, if I would only have Dijkstra to my disposal, then suppose that I have like 5,000 nodes that I'm interested to relate to 5,000 nodes, it will take like about 1 year to find only those distances or those travel times or whatever it is. So this is probably not good enough. Then you think, okay, well, I just understood one thing. This method computes that shortest path from here to there, but it also computes many others. And I'm interested on relating many points with many points. So why don't I do it from one point to all the other points that I'm interested in? Well, that's like doing that matrix one row at a time or one column at a time. Well, still, it will take about 3 hours before you would have only related 5,000 points with 5,000 points. And I can tell you, the number of households in a country is usually much bigger than 5,000. So this is actually not good enough. At some point, well, Dijkstra published these 3 pages in 1959. At some point in 2008, this gentleman wrote a PhD thesis, and there was also an article of about 1 or 2 pages in the Scientific American, which actually acknowledged that this gentleman was among the top 50 most influential persons or institutions in 2008 in technology. And why? Because he invented a way to compute shortest paths on road networks in ways that scale up with the size of the network, meaning that they do not get worse if the network is very big, not substantially worse. And actually, you can compute many queries, which is like from all the households to all the potential facilities in very efficient times. So this is the very first breakthrough in modern connectivity on road networks. And it basically means for the same size, like 5,000 times 5,000, that you can get it like in 3 minutes. Much better, right? Basically, what it did is that it looked at the graph, and now I'm looking at the graph that is around Amsterdam, and I can tell you that actually the ABS is more or less right here. A graph in the eyes of Dijkstra is very black and white. All these edges are equally valuable. In the eyes of the algorithm invented by Dominic Schultes, these edges are not all equal. They have different importances for computing shortest paths. And they are actually colored in a way that reflects that importance. In fact, the graph becomes hierarchical. You have like floors, and if you are on the ground floor, you have all the edges. If you are on the first floor, you have a sparser way to look at the same graph. On the second floor, even sparser, even sparser, even sparser. So there are, in these colors that I see here, there are maybe less blues and there are greens and things like that, reflecting that importance. And you could say, okay, I've seen that before. This is like a map, right? A map which classifies my segments as being either roads or highways. No, it's not the case. They may represent the highways because highways are indeed important to get you from one place to another very fast, but they were computed with mathematical properties that ensure that indeed the classification is correct to preserve the optimality that actually the method of Dijkstra will find. So this is a kind of a tricky thing, but very beautiful. And you can actually see that if you want to go from that place over there to that place over there, two places in the Netherlands, one being in Utrecht and one being in Zoetermeer, when you apply a method that has this ability of distinguishing the importance of edges, we are actually seeing what the method is doing to compute a connection from that specific point to the other point, while applying a Dijkstra, but not the Dijkstra in the pure form that is scanning all the connections from each node to each node that can be reached, but taking like bigger steps if the part of the network that was reached is indeed one of those important ones. So you see that you can have like edges colored because they were scanned, while there are many other edges that are not colored at all because they were just ignored for good reasons, and that enables the method to be much faster. And in fact, when you want to compute this accessibility on a network, you end up doing it simultaneously from different sources to different destinations. And that's what is being illustrated here for a single connection, but being computed from both the departure and arrival node. And that's more or less the key to having like many-to-many computations, or let's say the accessibility between the list of possible locations and all the households in some sense. Right, so this is a very brief explanation of what happened since Dijkstra invented this beautiful method to nowadays. I highlighted a method called highway node routing. It's not the state of the art. There are more sophisticated methods nowadays. One of them is called contraction hierarchies. And the interesting part is that such very powerful methods are available to everybody that programs in Python, because a package, which is in this case called Pandana, actually includes the contraction hierarchies algorithm in it in a way that enables deploying it within Python. And this is actually one of the packages used by PISA when we need to model our own road network. For instance, when we dealt with the need to decide where to install hospitals in the country Timor-Leste, we faced the situation that in Timor-Leste, the available road networks were not good enough to have proper accessibility metrics. So we had to stitch some networks together, like a network that is publicly available within the OSM data set, with a network which is not publicly available, but is available from the government of Timor-Leste. None of them is good enough, but like the merging of both with some additional processing, became good enough for the analysis, but we were actually dealing with the network itself within PISA, meaning that we had to compute all these shortest passes there, and that's using Pandana. So this is an example of what an optimization problem means for accessibility. That optimization problem is the shortest path. And when you know about it, you understand, okay, there is a model, which is a network in this case, there is an algorithm, and there is a kind of a notion that what the algorithm finds is the optimal unbeatable solution for this specific question, which is how can I go from one point to another point, how long it will take, or how far is it? All right. As I said, there is this notebook that illustrates how to use Pandana and so forth. Okay, but I said this is what we need to do when the country does not have a very good publicly available digital map. If indeed a country has, then it's very likely to be the case that professionals, like for instance Mapbox, will have a good coverage of that country. If we open this demonstration page of Mapbox, it brings us to a place in United States, in the island of Manhattan. And if I just put my point of interest somewhere, I see these isochrones being drawn immediately. And that's one of the things that indeed such a professional service can do for you. And in this case, I have an isochrone because I'm interested on travel time. I'm interested on the points that are 10 minutes from this destination. I can also ask myself what is the distance on the road network of this specific place on Earth, which is part of the island of Manhattan. And if I have like 1,000 meters, then this is indeed what is within 1,000 meters of that destination point. And I can do this for different modalities. I've been doing driving with traffic. I can just do driving without traffic. And you can see that it is indeed different because it means that the information available to this service in terms of what is the congestions observed on different points of Earth are indeed reflecting on this accessibility, which is very important. It's available to us, it's available to PISA, and it leverages the ability to compute these catchment areas towards levels that are beyond computing shortest passes between pairs of points, because you can get these sets right away. And if you have these sets, then you can select what are the points within the metric of access of your interested destination or not. All right. So when indeed a service like Mapbox or Google Maps or whatever offers enough accuracy, we just use it. All right. So this first part of my talk dealt with trying to explain what is behind the question, am I within reach of my point of interest or not? Being within reach defined as within some distance, a real life distance on the road network available to me, or within some travel time. So I related that to the so-called shortest path problem. I explained you how mathematics solves it by first translating the reality into a network, and then on that network applying an algorithm that is guaranteed to find the optimal solution. I told you that this very old algorithm already got a lot of improvements that make it much faster on the road networks, and that there are professional services like those of Mapbox that give you the ability of getting so-called catchment areas, which can be those isogones or isochrones, which are those areas within which points are within the access metric that you specify. So if you say, okay, I want to have hospitals installed in such a way that they cover as many people as possible within 1 hour access of those hospitals, that is what we are interested in. Now, suppose now that we have such catchment areas. And now I have here a very random instance drawn in the way like we draw them on our whiteboards, on our boards, on our papers, on whatever. So we tend to do it very stylized like this. So I have like these blue dots are some households where there are people, and these squares in red, numbered from 0 to 4, like these 5 squares with some numbers on it, are the potential locations for facilities that may or may not be installed. And the circles around these points are the catchment areas, which in this example are just very stylized circles, just to have it easy to understand. I can see here that I have all these potential circles that I can select by opening a facility, and if I open them all, I end up covering everybody, which is indeed in this small instance of mine. The numbers here reflect, let's say, the total number of households. Now, for the sake of simplicity, each household counts as one person, so I have like 15 potential users of my facility within reach here. None of them is served because I did not open this one. 15 of them are not served with a total of 15. And in this case, I did open all of them. So this one serves these 15 that are within reach and so forth. So this is actually what we end up dealing with. This is an example of one of those instances, and those instances of which problem? The problem of selecting where to open potential facilities in such a way as to serve as many interested people as possible. In this case, I only draw, let's say, the case that nothing is open, thus nothing is available, against the case that everything is open, everything is available. And what I'm looking for is typically something in between. So I have like some means, some budget, something that limits the number of facilities that I can open. And I want to find the best subset of the potential facilities, and what is best in such a way that it ends up serving the highest number of people within that accessibility metric, which is represented here as the circles. So it's a new optimization problem. The problem that we have discussed before, like this shortest path, was only used to kind of become a preprocess for this problem. So I had all this data. I had the data like the road network itself, the location of all these households. I know where my persons are in that specific area of the globe. I know where I may or may not install facilities. Those are those red squares, the potential locations I can select from. And I am able to preprocess all this data into, let's say, the information which is here represented by these circles around the potential locations and the points inside those circles. I did draw them as circles in my example, but in fact, whether the catchment areas are circles or any other sets does not change what happens afterwards, because what I end up having is information that can also be seen as this picture. Is a different way to represent exactly the same situation as here. I have now on the rows of this matrix the potential facilities, on the columns the households, and what I see here is that, for instance, the first household can go to the first facility and to the third facility. It's within reach of those, and so forth. So I see here another representation of the same reality as here. It depends on what you consider as a good representation, how you think about the problem. So you are either selecting which of these circles to select in such a way as to cover as many points as possible, or selecting which of the rows on this matrix to select. And in this example, I select the second and I select the fourth row, and I see that the union of those being served is here. And I can also see that if I select all of them, I serve everybody. But I want to select that subset with the highest total head count. Well, that's a new puzzle. I can tell you one thing. If you find an algorithm that can solve this puzzle efficiently, like Dijkstra found an algorithm to solve the shortest path efficiently in 1959, well, efficiently means that you can actually do it in a reasonable amount of time, regardless how big your puzzle instance is, then you are entitled to receive $1 million because there is somebody willing to pay you $1 million for that. Well, actually, the true story is you can also get the same $1 million if you prove that such an algorithm does not exist, but that is another story. In fact, this is a difficult problem, much more difficult than the problem of finding the shortest path between 2 points given a road network. But we solve it because we need to solve this problem in order to find the optimal locations where to install facilities to serve as many people as possible. And as I said, regardless of your selection of accessibility metrics and how do your catchment areas look like, it ends up becoming data like this. I have, for the same example that we have been seeing, I have these 5 potential facilities, and I have these lists of households that are within reach of those potential facilities. And I've seen 2 representations of the same reality, like the one with the circles, the one with the matrix, and the black squares and the gray squares, all that stuff. And I have here a representation which is just data with indices, very anonymized. 0 to 4 are the potential facilities, 0 to 29 are the households, and I have like these lists. And an algorithm that could actually find the best selection of lists that yield the highest, let's say, union of the numbers in it is what we are seeking. Well, it's not easy. This is actually the same information but transposed, from the households to the facilities within reach, meaning that I'm either looking at the information on the rows of this matrix or on the columns of this matrix, exactly the same instance. It's not easy to do it. It's a very difficult problem to solve, but there is something that enables us to translate this specific question by means of a way of encoding it into in a so-called mathematical optimization problem, which enables us, and PISA as well, to resort to the power of very sophisticated solvers. And that's exactly what the book I mentioned you is all about. It tells you how to do this magic of coming up with a mathematical model for some reality. And there is a part of that book about location models, example 3.10. There is also a notebook that complements that. And there is exercise 3.1. Well, you probably will think, well, I came to a cafe and somebody gives me an exercise. Well, don't worry, the exercise is solved at the end of the book. And that exercise deals with exactly the same problem as locating the best subset of facilities in order to serve the highest number of people, as PISA does for instance, hospitals or COVID test centers or whatever, or water wells or whatever. And again, it all started with a classic. And the classic is, in this case, a paper called the Maximal Covering Location Problem, which is not that old. This one is already within my lifetime. 1959 for Dijkstra was prehistory for me. This is within my history. 1974, also very cited, a little bit longer than the paper of Dijkstra, but basically it came up with this model. And now you see a lot of mathematics here. Those that are a little bit faint of heart and you think, okay, what is this all about? Maybe you can go through the book that I mentioned and get a little bit an idea what is this actually telling you. But this model is so small that I will attempt to explain what it actually means. And why is it important to understand such models? Because this is the intermediate language in between reality and whatever you use to solve problems, which is in the case of PISA mostly Python, there is this intermediate language, which is mathematical modeling, that enables to translate reality into something that can be fed with data, translated into an optimization problem that will be solved by a solver, and that yields you indeed the solutions that you are looking for. In this specific case, and I can tell you, this is exactly the story that we have seen with the circles, with that matrix, and with those lists of numbers. I have two decisions that I need that the solution will take for me. One decision being represented by X, and one decision being represented by Y. Well, Y says that a specific household, an household indexed in I, is going to be served yes or no. And for each household, my data tells me what is the head count, that's that Wi of Yi, that head count will be served if this Yi is indeed being reached. So this Yi is the location where a household of count Wi is placed, and I want to have as many of those locations as possible in such a way that the sum of the head counts is maximized. That's actually what this thing says. That's what we call the objective function. And then there are so-called constraints that represent the logic of the problem. The logic of the problem is, in this case, twofold. It says, okay, I can only install as many facilities, like hospitals or whatever, as I have in my budget. So these X's are the same thing as the Y's, but not for the households, but for the facilities. So basically, I'm now dealing with the blue dots are the households, those are the Y's, and the red squares are the facilities, those are the X's. So I will install only up to B facilities. So my sum of those X's that are set to 1 cannot exceed B. And I can only say that my household is served if at least one facility is within reach. So if I am looking from the perspective of this matrix here, an household is served if there is one, let's say, of these potential facilities in the same column, which has been selected, like in this case. And here I have even 2 of those that were selected. And for this one, there were 2 potential facilities, but nothing has been selected, so it's not served. So we see here how the household variables, which are represented by the Y's, can become 1. They can become 1 if, when we look at the column of that representation over there on my previous slide, at least one of the X's has been activated or selected or set to 1. So this is the way that we translate our problem of deciding where to put all these health centers, for instance, into mathematical notation, and then this translates into Python more or less automatically. It's not so difficult, and there are plenty of examples online in that companion I've showed you, and then you only need to solve it. And then there is always good news, and I would like to finish with good news. Nowadays, despite the fact that this problem is indeed of a very different nature as the shortest path, namely for this specific problem of finding the best subset of locations to open in such a way that all these households are served, that problem is very, very difficult to solve. But nowadays there are very, very powerful solvers, one of them Gromicho, and Gromicho is not only powerful, but also kind enough to make the powerful solvers that it produces available to ABW, including to PISA. So these solvers are such that we can solve instances of this problem with many, many thousands of households and many, many thousands of potential facilities in just minutes. And well, that's great for many countries. If you read our reports on what happened in Timor-Leste, Gromicho was more than enough over there. And for some cases with some choices or where to install the facilities for the stroke centers in Vietnam, it was also enough.
But in Vietnam, if we want to have a much higher collection of potential facilities, it becomes beyond reach of Groby. And that meant that we had to develop other methods, so-called heuristics. What are heuristics? Are algorithms that try to find very good solutions, but will not be able to tell you in the end, there is nothing better. This one is optimal. But heuristics are very beautiful things to talk about, but I think it is beyond what we can serve on this cafe today. So who knows, we can maybe talk about that on another occasion. Before I finish, I'd like to tell you that PISA does more than only deciding subsets of locations to install, like health centers or to dig water wells or whatever, which use road networks to decide on the accessibility. PISA also does things like finding the best path for such a contraption. The contraption that we are seeing here has been created by the company called Ocean Cleanup, and it's used to actually go through the waters of oceans in such a way as to collect as much wasted plastic as possible that is floating there. So it's a contraption that is actually used to collect the wastes that ended up in the oceans, huge amounts of plastic. And the problem that you may already imagine is the oceans are huge. These things don't go very fast. And in the end, you want to collect as much plastic as possible. Well, the ABW, and it's becoming part of PISA, has already been able to devise an algorithm that can, using the data available to it, and the data available to it are estimates of the density of plastic in these big oceans, can find routes like this one. Well, how is this actually done? There is a paper that you can read. That paper has even been awarded a very nice prize, and it explains actually how you optimize the path towards plastic-free oceans. And that paper is not based on the things I have explained. It introduces yet another very important methodology within mathematical optimization, which is called dynamic programming. And that's also maybe for another cafe. It's not possible to serve today. May you like to read about dynamic programming, you can Google about it. There are many, many interesting sources. There are many sources on the paper itself, but I like just to suggest another one that you probably will not find just by Googling it. It's, in my opinion, a very well-written PhD thesis with very interesting things about dynamic programming, including very easy to read explanation how it works. Okay, so this is what I cooked for you today and served on this cafe, with my assumption that the public would be very diverse, a public that did not know anything about mathematical optimization at all, public that did know a lot about mathematical optimization, but maybe a little bit less about what you can do with it. So I don't know, shoot at me and tell me, what did you think about what I've served you? I will stop sharing my screen if I find the button. There it is. And I'm looking forward to hear whatever you like to tell me. Any question? Any suggestion?
Awesome. Thank you so much.
Any coffee anymore?
This was very great. And I see lots of clapping in the chats as well. So big virtual round of applause. We'll open up.
They are clapping their hands and not trying to clap at me. That's all.
Yeah.
Open for debate. All right.
So if
tell
there's
me.
Any questions, you guys can raise your hand and we'll take any questions now. You can also put them in the chat if you prefer.
You can, I think you can unmute, right? So it's not a very huge group.
Yeah. Does anyone have any questions?
Any questions, any feedback, any remarks?
Okay, I think it was very clear.
That's one interpretation. Let's hope that's a good one.
Okay, maybe
Yes.
I could just give some feedback. Thank you so much, because it was an outstanding presentation. So obviously I'm familiar with these algorithms for Dijkstra for the mass covering problem. I actually had the pleasure and the privilege to work with Professor Church at the University of California. But your presentation was really very clear, especially for the young people here in the audience. It was really excellent to see the applications and hearing about the complexity, but how you can overcome it and how it has been embedded within PISA. So I'm really looking forward to work with PISA more closely.
Thank you very much, Paola. I'm pretty sure that you know very well what is a good pizza when we spell it a little bit differently, of course. But let's hope that you will enjoy working with pizza. And thank you very much for your very kind feedback. Any questions? Any other things you like to share? Oh, there is a chat. Wait. Let me see.
Yep, Yvonne says, thank you very much. I don't have any questions right now, but nice to see that these are algorithms applied in real life. Boss says, thank you. And Stacy says, thank you for the cafe session. Really informative as an area I don't normally work on. So I think if there are no other questions, then we can.
May I
yeah, please go ahead.
contribute? Hi, Joaquim.
Hi, Isabel.
Isabel here. I was just wondering if PISA would fit the problem of, for instance, home healthcare services. Like I'm working with a nonprofit that provides this service to the elderly, and it seems like we also work with a network, a graph that represents the network of the location of the houses of those that receive the service. Would it fit the PISA framework?
Depends. I do not understand
Of course
exactly what the problem entails. Sometimes when you are serving elderly, you travel to the homes of those. And not only you need to be there, but you also are concerned about the routes that you make in order to serve more than one.
Yeah.
So it becomes a problem of not only location, but also routing.
Yeah.
But the good news is that we are adding such capabilities to PISA because we also have situations, projects that we are working on that deal with vaccination and other interventions traveling. So I think that the pizza that you would clone if you go to the GitHub right now and you get it into your machine will not be at that level yet.
Okay.
But we are moving towards a location combined with routing. So that may be interesting for you. And what a pizza is a community effort within the ABW, and which grows mostly because we get aware of problems and we get people that help us. So I think that what you are sharing with us is also an opportunity to see how we can together make it happen.
Oh, it will be a pleasure to work with you on this topic. So let's keep in touch and see what comes up of this collaboration. Nice to see you, and thank you very much for your presentation, Joaquim.
Thank you, Isabel. Good to see you again. All right. So in that case, I think we are reaching the end of the time allotted for this cafe. It has been recorded. Recording will be made available